Okay, let's dive into this. Have you ever seen your computer do something that just feels wrong? Like really fundamentally broken? Today, we're hunting a ghost in the machine, a phantom that makes computers fail at the simplest, most basic math.
I mean, seriously, look at this. You ask a computer, a machine built for calculation, to do first-grade math, and it spits out this nonsense. Your first thought is probably, that's a bug, right? But what if I told you it's not a mistake? What if it's doing exactly what it's supposed to do?
Yeah, this isn't a bug. This is what happens when you have a fundamental difference in how we, as humans, and computers actually think about numbers. It's a clue that we're dealing with two completely different ways of seeing the mathematical world.
You know, the best way to understand this is to think of it as a language barrier. It's like we're speaking one language and the computer is speaking another. And, well, just like with any translation, sometimes things get a little bit lost along the way.
So here are the two languages. Our entire lives we've thought in decimal, or base 10. It feels natural because we have 10 fingers, so we use 10 digits, 0 through 9. But computers, they only speak binary, or base 2. Their entire universe, everything they do, is built from just two little symbols, a 0 and a 1.
So where does the translation break down? Let's zoom in on a number that seems incredibly simple to us, but for a computer, it's a total nightmare, and that number is 0.1.
To really get what the computer is going through, let's think about a number that gives us a headache in our own decimal system. You probably remember this from school, right? Trying to divide 1 by 3.
And what do you get? This, an infinitely repeating decimal. It just goes on and on forever. You can write 3s for the rest of your life and you'll never ever reach the exact answer. So what do? You have to round it, which means you're always leaving a tiny little bit of error behind.
And that right there, that's the aha moment. For a computer, trying to represent 0.1 in its binary language is the exact same problem. It becomes an infinite repeating fraction. To a computer, 0.1 is their version of our 1/3.
So why? Why is it such a problem? Well, it's because a computer can only build fractions by adding together these very specific building blocks: halves, quarters, eighths, sixteenths, and so on. It's like trying to make a dollar using only quarters and dimes. You just can't make exactly 73 cents. You can get incredibly close to 0.1 by combining these binary fractions, but you'll always have this tiny, tiny leftover piece.
Okay, so how does the machine actually try to build these numbers? This is where our human intuition often trips us up, but once you see the logic behind it, it's actually kind of beautiful.
Here's a super common point of confusion. We're used to seeing numbers to the left of the decimal point, where everything gets bigger. 1, 2, 4, 8. But the very moment you cross that little point, the whole story flips. The powers of 2 start dividing, and the values get smaller and smaller and smaller.
Just look at the pattern here. It's so elegant. As we move from left to right, the power of 2 just decreases by 1 each time. It goes from 2 squared to 2 to the first to 2 to the 0, and then it doesn't stop. It just keeps on going right into the negatives. -1, -2. It's one single, unbroken mathematical rule. So why does this feel so weird to us? It's because our brains are wired to think of graphs, where things get bigger as you move to the right. But with numbers, the most valuable digit is on the far left, and they get less valuable as you move right. It's that internal conflict, that clash of directions that makes the computer's simple logic feel so counterintuitive to us.
So let's just walk through it one more time. You start with 2 squared, that's 4. The exponent drops by 1. You get 2. It drops again, you get 1. Now you hit the decimal point, but the pattern just keeps on trucking. The exponent drops again to -1, giving us 1/2. See, there are no new rules, no special cases. It's one single, unbroken, logical pattern. So, the key takeaway here is understanding this system. It explains the ghost in the machine. But you might be wondering, does this tiny, almost microscopic rounding error actually matter in the real world?
Oh, it absolutely does, 100%. In financial systems, that tiny error, repeated millions of times over millions of transactions, could mean the difference between profit and total bankruptcy. In science, it could be the rounding error that sends a billion-dollar rocket slightly off course. It's the gap between the clean, perfect world of abstract math and the messy, physical reality of a real-world computer.
And you know, the key to this whole system, the thing that explains all of it, lies in a tiny detail we've been looking at this whole time. This little piece of mathematical notation right here, a 2, with that tiny little -1 floating about it. It seems like such a minor detail, doesn't it?
But we just saw how a tiny rounding error can have enormous consequences. So what happens when our human intuition gets a fundamental piece of notation like this wrong?
In our next explainer, we're going to talk all about negative powers, why a tiny error in understanding this notation really matters, and what strange anomaly happens because of it. It's a fun one. See you then.